In this episode of Remote Calculus, we will be looking at finding volumes of revolution by using the shell method. What we mean by a volume of revolution is picture a solid formed by revolving a curve around an axis and imagining the solid that would be formed. I have an example of a solid made on a rapid prototype machine, and that solid was formed by revolving this sideways parabola around the y-axis. Now we could find this volume with disks or shells, but we're going to focus on shells in this particular video. What we mean by a shell actually starts off as a box. You want to picture a very thin box, and if you wrap the box around, it will form a shell. The volume stays the same whether it's wrapped around to form a shell or whether it's flattened out to form a box. And you're imagining these shells stacked very tightly within each other, forming a solid. So in the center, where the peak of my solid is, the shells are very skinny and tall. And then in the middle, there you have medium height and medium radius. And then out towards the sides here, the height of the shell is very short and the radius is fairly big. So that's how you want to picture, like you want to picture the shells out here being like a short band, and then the shells in the middle are kind of more, a suitable shell, and the shells in the center here are more like a straw. And you're picturing them packed really tightly together to form your solid. So we are going to be adding a whole bunch of these shells together, and in fact we want to eventually take the limit as those number of shells is going to infinity, and thus the shells themselves are getting infinitely thin. So that's the whole idea of an integral. An integral is an infinite sum. And we want to program our integral to calculate exactly what we're trying to find. And here we're trying to find the volume of a bunch of shells. So I need to write down an expression that gives me exactly the volume of a shell for this particular shape that I'm trying to form. So again, it starts off as a box, and a box has volume, length. So the length is this side, and the width, and then the height is how thick the shell is. I have a can coulis here, so it's the thickness of the can coulis. So length times width times height is the volume of the box, and when I wrap it around, it will still have the same volume as my shell when I wrap it around. So in terms of a shell, what was the length of the box becomes the circumference of the shell. A circumference of a circle is 2 times pi times the radius of the circle. What was the width of the box is now the height of the shell. It's how tall the shell is. And then the height of the box is the thickness of the shell. So length is circumference, width of the box is the height of the shell, and height of the box is the thickness of the shell. So looking at our shape here, again, here's our shape. The radius of our shell, which we need because we're going to find the circumference, the radius is a length, and the length will be the difference between whatever x you've stopped at and this lower side of the length. Well, that's on the y-axis where x is 0. So x minus 0 is x. That's my radius. So my radius is x. That's the length of this segment that I've drawn. The height of the shell is the difference between this upper y value and this lower y value. So upper y minus lower y is the height of the shell, or the width of the box. So I want to write down the difference between the two functions. So this is the function that's forming the upper part of the shape, And this is the function that's forming the lower part of the shape. Notice they're basically the same function, except for I have positive 1.5 times the square root of 2 minus x over the square root of 2. And for the lower function, I have negative 1.5 times the square root of 2 minus x over the square root of 2. And then those expressions are added to 1.5. And then the thickness of the shell was the height of my box. So the thickness is the entity that we're imagining becoming thinner and thinner and thinner as we make our shells more and more numerous. So double check that you've written down exactly what you're trying to find. We're trying to find the volume of a shell. This is the circumference of the shell, 2 times pi times radius, and my radius is the difference between x and 0, so x minus 0 is x. And then the height of the shell is the difference between upper y and lower y. So I'm taking the upper y function and I'm subtracting the lower y function. And then the height of the box is the thickness of the shell, and that's represented by dx. Every single thing means something. You don't write anything down that doesn't mean anything. So like this dx kind of just seems like it's added on notation. It's not. It's actually representing part of my shape. It's the thickness of my shell or the height of the box. X is my variable, and so the lowest x value is 0 and the highest x value is 2. I know it seems like when you picture it revolved, you might be picturing negative x's over here, but you are defining x in terms of the shell, and the radius of the shell is going from the y-axis to x here. So the lowest x that I would consider would be 0, and the highest x I would consider would be 2. So 0 is my low limit, 2 is my upper limit. Now the fundamental theorem of calculus tells us that one of these integral values is equivalent to the antiderivative of the function evaluated at the upper limit and at the lower limit, and then you take the difference in those two values. You actually want to consider that we're finding a volume, but numerically this volume is equal to the area under this curve. By the way, if you clean up this messy expression, it cleans up fairly nicely to the expression I have down here. Notice the 1.5s cancel out, and if I subtract this -1 times 1.5, it's a match to this expression, so I have 2 of those expressions. And then 2 times 2 is 4, 4 times 1.5 is 6, and 6 times pi divided by the square root of 2 is just a constant multiple that's multiplying the function. So I factored out all the constant multiples, that's what this is, and then I'm left with x times the square root of 2 minus x, and then dx. So the area under this curve is equivalent numerically to the volume I'm trying to find, not in terms of units, but in terms of the value. So for example, if we look on our calculator and I've typed in the volume expression, but I'm graphing this function. I'm not graphing these functions right now. I'm graphing the function that represents my volume, and I get this shape. The area under the curve of the volume function is numerically equivalent to the volume I'm trying to find. So again, if I run the integral program and I say lower limit 0, upper limit 2, it's already shaded in, but it's shading it in again, and it will give us our value 20.10. So the volume of this shape is 20, just about 20, a little bit more than 20 cubic inches, but that's numerically equivalent to the area underneath this curve. This is actually a nice integral to work out by hand. It has a good example of U substitution. So if we wanted to actually work it out by hand, notice I have an interior function here, 2 minus x. And if I replace 2 minus x with the simplified variable u, then the derivative of u will be -1 times dx, or -1 times du is equal to dx. And u would also yield u minus 2 equals -1 times x. So I'm just algebraically taking this and rewriting it. If I then multiply this side by -1 and that side by -1, I get 2 minus u, so I reverse the subtraction, is equal to x. Then you substitute exactly. So notice the constant multiple is just going along for the ride. X is 2 minus u. So there's x. Then I have the square root of u, because u was 2 minus x. So I put that in. And then dx is -1 times du. So everything in this expression's been substituted and accounted for. Then if I distribute the square root, I have a fairly straightforward power rule application. So applying the power rule of the antiderivative is I add 1 to the power, so 1/2 plus 1 is 3/2, and then dividing by 3/2 is the same as multiplying by the reciprocal, 2/3, and then 3/2 plus 1 will be 5/2, and dividing by 5/2 is the same as multiplying by the reciprocal, 2/5. And so I get this expression is just my constant multiple. 2 times 2 is 4, so 4/3. 2 minus x is now replacing u, because I started off with x and not u. And that is raised to the 3/2 power. And then minus, again, the u is getting replaced back with 2 minus x to the 5/2 power. By the fundamental theorem of calculus, once I find my antiderivative, that's what this is. This is the antiderivative of this function. I plug in the upper limit of 2, and I plug in the lower limit of 0. 2 minus 2 is 0, 2 minus 2 is 0, so that turns into a 0. And if I carefully type this in my calculator, I get the 20.106 that we saw in the shaded area on the calculator. So again, it was a nice one to kind of work out by hand, seeing kind of a clever use of U substitution. It may seem like this shape is kind of small to actually fit 20.106 cubic inches in it, but if you picture having picture a can that had a radius of 2 and a height of 3, the volume of that can would be the area of the circle, so pi r squared. If my radius was 2, it'd be 4 times pi, and then the height of 3, that would be 37.7. So we've trimmed off some by, there's no volume up here, no volume up here, so it makes sense that it should be about 20.